We have finally come to the last section. Well, there's a little bit of an extra part with fermentation, but the last section of cellular respiration, which is oxidative phosphorylation. 2 parts: electron transport, chemiosmosis. All right. This process, which is finally, we are at number 3 in the cool purple of cellular respiration, okay? This is going to make 90% of the ATP that we need, okay? Our main objective in this chapter is to learn how cells harvest the energy of glucose and other nutrients in food to make ATP. The metabolic components of respiration we have examined so far, glycolysis and the citric acid cycle, produce only 4 ATP molecules per glucose molecule. 2 in glycolysis. Remember, 2 are invested, and it creates 4, so you're only getting 2 net. And 2 in ATP from step 5 from that thing called GTP, and that S-level phosphorylation, okay? That's where we are getting our 4, okay? They're all from S-level phosphorylation, okay? That's an important part here, is that S-level phosphorylation. Maybe I'll underline that they're both from the same process, which we have written as an enzyme transfers a phosphate group from a substrate molecule to A delta P, okay? All right. At this point, molecules of NADH and FADH2 account for most of the energy extracted, which we know because we have 2 NADHs sitting in glycolysis, and we got friggin' 8 of them from the citric acid cycle, all right? So we have 10 ready to go. And we have those 2 FADHs from the citric acid cycle, okay? So let's remember that. These electrons escorts link glycolysis and the citric acid cycle to the machinery of oxidative phosphorylation, which uses energy released by the electron transport chain to power ATP synthesis. The electron transport chain is a collection of molecules embedded in the inner membranes of the mitochondria in eukaryotic cells. Okay. Let's find out more. What's happening here? The electron transport chain has several types of cytochromes. Most of the remaining electron carriers between... Let's just read slowly here. The folding of the inner membrane to form cristae increases its surface area, providing space for thousands of copies. Okay. Electron carriers alternate between reduced and oxidized states. NADH, electron carrier. I'm pretty sure FADH is an electron carrier too. It's switching between NAD plus and NADH. This electron shuttle, okay? Each component of the chain becomes reduced when it accepts electrons. Reduction, GER, gaining electrons, reduction. We know that. It then returns to its oxidized form as it passes electrons to its downhill, more electronegative neighbor. Let's take a closer look at the electrons as they drop in energy level. Okay. Complex 1 in some detail as an illustration of the general principles. Electrons acquired from glucose by NAD plus during glycolysis, electrons acquired. Citric acid cycle transfer from NADH to the first molecule of the electron transport chain. This molecule is a flavoprotein. Electron carrier is a small hydrophobic molecule. So the remaining electron carriers between are proteins called cytochromes. FADH2, the other reduced product of the citric acid cycle. A reduced product of the citric acid cycle. Reduced product. Electrons are transferred, gain of electron, reduction. All right, are transferred to FADH. This is a reduced. Okay, that makes sense. Electron transport chain makes no ATP directly. Okay, that's important to know. The electron transport chain the electron transport chain makes no ATP directly. Good to know. What's our instead here? Instead, it eases the fall of electrons from food to oxygen, breaking a large energy drop. Okay. Eases the fall of electrons. It eases. So it's almost like a firefighter catching, you know, I got you, and it bounces to the next one, all right? It eases, I like that, it eases the fall of electrons breaking a large free energy drop. Free energy drop into a series of smaller steps. 2 small steps. Right? It's like a like a firefighter. So let's see. We're not at ATP synthase yet. It basically has these 4 modules. So electron, so we have electrons from NADH. These figures, there's a lot in these figures I'm learning. A lot. Mom? From NADH or FADH2 or FADH2 move from a less electronegative carrier to a more electronegative electron further down the chain. Electron carrier down the chain. All right, electrons from NADH move. FADH2. FADH2 is losing those H's. NADH is going to NAD+. And oxygen is the last step here. Oxygen is last in the chain. NADH least electronegative. So NADH, which we picked up in citric acid cycle, least electronegative. And it's going to go through 1, 2, 3, and 4. And then it's going to go to oxygen. It's in its diatomic state. Oxygen's very electronegative because look how close it is to fluorine. Most electronegative. Okay. Now, what is chemiosmosis? Let's see what it says about electron transport chain at the very end. And there's some water there too, okay? All right, chemiosmosis. This is like, it's pretty involved here. Okay, so along the transport chain, so now we are working with the inner membrane space here, okay? So along the chain, this electron transfer causes causes protein to move H plus from the mitochondrial matrix to the inner membrane space. I'm going to say inner membrane there, okay? Storing energy, this stores energy as a proton motive force. That's proton motive force. Or we can call that a gradient. An H plus, which remember, H plus is a proton. H plus gradient. I know there's a lot of words on here. Back into the matrix. So basically, I guess I could kind of draw this. Basically, what color do we have for lipids? Lipids are blue. Basically, you have your membrane, and you have some proteins. You could probably just draw this. We have one. One underneath. We have 3. And then we have 4. All right, and then we have this big mama jama over here. All right, and this is in our lipid bilayer. This is going to take, well, whatever. Record this. This is on the bottom. All right, and we want to put little yellow. I don't really have yellow. They're always yellow though. Will this one work? I think I did have yellow and I just kind of got rid of it. I guess you could do orange. Ba bum 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 boom bam bam boom bam bam boom bam bam. Use the same consistency though. Let's do, yeah, we'll do orange, whatever. These are our tails. All right, there's our lipid bilayer. We have 1, 2, 3, and 4. One, 2, 3, 4, and our last one here is our this is our ATP synthase. All right, and basically what is happening here, we found that what was happening here and this area here, this is our mitochondrial matrix, right? This is the mitochondrial matrix. And up here is our intermembrane space. And what's happening and this is our mitochondrial membrane, okay, is that our protons are being pushed out. Right? H plus is coming out against this gradient. These like pump, I guess, are these protein pumps? 3 and 4 too. All right. Our FAD is involved here, and our FAD, which is from the citric acid cycle, is kind of chilling. FAD. All right, that's kind of chilling down here. But we have all these protons out here. And the protons are coming back through all right? But as this comes through, this is like driving this like a turbine. and ATP is coming out. All right? And that's turning this, right, like a turbine. All right, and a shit ton of it too. A lot of it is coming out of there. It's using the exergonic flow of electrons from NADH and FADH2 to pump H plus across the membrane. All right, our NADH is over here too. So this has something to do with it. Okay. This part, this is our chemiosmosis. All right. This that's our chemiosmosis down here. And this is creating 28, 30. This is creating about 28 ATP. 28 of them. 28 ATP. I don't know what else really comes out of it, but glycolysis, 2-NADH, pyruvative oxidation. This is saying, well, 2-NADH or FADH2. What do you mean by that? Citric acid cycle, 6-NADH. This says 8. Yeah, 8 there. 2-FADH2. You got 2-NADH kind of coming out of nowhere. I don't know. But that's pretty much it. Efficiencies, even the most efficient automobile, 34%. That's pretty much all I have here, if I'm being honest. Chemiosmosis is an energy coupling mechanism that uses energy stored in the form of an H plus gradient, whoop, whoop, across the membrane to drive cellular work. In mitochondria, the energy for gradient formation comes from exergonic redox reactions along the electron transport chain, and ATP synthesis is the work performed. But chemiosmosis also occurs elsewhere and in other variations. All right. Certain members of the electron transport chain accept and release protons along with electrons. The aqueous solution chain is an energy converter that uses the exergonic flow of electrons from NADH and FADH2 to pump H plus across the membrane. H plus has a tendency to move back across the membrane, diffusing down its gradient. The ATP synthases are the only sites that provide a route through the membrane for H plus, as we described previously. One last review of this whole goddamn cycle, okay? I eat a piece of sugar. Glycolysis happens in the cytosol of the cell, can happen without oxygen. The quick and dirty, that breaks it into 2-pyruvate, all right? It's costing 2 ATP to get this whole shindig started. 4 are created, but we have a 2 net, all right? We're also creating 2 NADH, these electron carriers, which are gonna be important, okay? But that 2-pyruvate, or glucose, is a 6-chain sugar, cleaving into 2, 3-chain sugars called pyruvate. They have a negative charge. They are actively transported from the cytosol into the matrix of the mitochondria. Here, they have electrons. They want to lose those electrons. That is oxidation. That's why the 2A is pyruvate oxidation, okay? They are converted through this into a couple of different things. A little bit of CO2, because that 3-chain pyruvate turns into a 2-chain acetyl-CoA, which is that 2-carbon chain, is that acetyl, which we'll get to in a second. That's where that NADH comes into play. So we got 2 of them because there's 2 pyruvates. All right, citric acid cycle. All right, what are our products or our reactants? We have 2 pyruvate, we have 2 acetyl-CoA, okay? Still in the mitochondrial matrix. This is like part 2 of pyruvate oxidation. Basically what's happening here is the breakdown of glucose to carbon dioxide is complete. That acetyl group, that 2-carbon chain, is going to be added to an oxaloacetate, which produces that citrate, which produces that citric acid, okay? For each of those acetyl groups, which we have 2, because we have 2 pyruvates, 3 NAD plus are reduced to NADH. So then we have 6 NADH plus the 2 NADH. From pyruvate, we have 8 NADH, okay? 10 if you want to add it in from glycolysis. All right, those acetyl-CoAs, all those NADHs, also some CO2 is going to be released, but we've already accounted for that in our pyruvates, okay? Couple of different steps going on. That first step, though, is that citric acid part. That is the first step of the citric acid cycle. All right, a couple other steps that are important. Why it's called a cycle, the next 7 steps after that is going to decompose that citric acid back into that oxaloacetate, hence why it's called a cycle, okay? Step 6 is important because electrons are transferred to FAD, which becomes FADH2, which is going to be important in the electron transport chain, oxidative phosphorylation. Step 5 is where GTP is produced, which can make 1 ATP. Multiplied by 2, because remember we have 2 pyruvates, 2 acetyl-CoAs going into this. 2 ATPs from citric acid cycle, 2 ATPs from glycolysis. 4 added to the 28 of oxidative phosphorylation is our 32 total, okay? Steps 3 and 4, CO2 is produced 1 per, so that's 3, and 4, that's 2. That's 4 CO2, 6 CO2 total coming from the citric acid cycle. So, the other important thing is our ATP is created by S-level phosphorylation. Phosphorylation is creating our ATPs always, okay? So we're moving into oxidative phosphorylation. We have all these NADHs, all these FADHs, these electron carriers ready to oxidate, ready to reduce, ready to redox, okay? And that's going to drive this electron transport chain, okay? Makes no ATP directly because you need to get to this part, the chemiosmosis, which is rotating because of that. All those electrons we've gained are spinning that rotor and spinning that rotor. It's like a hydroelectric dam, and it's cranking out all this goddamn ATP, 28 of it to be exact, okay? The electron transport chain, though, this part from 1 to 3 to 4, it's breaking the large free energy drop. You have all these electrons coming in, and it's catching it like a firefighter to ease it into smaller energy releases, okay? Here's our NADH and our FADH2. They're moving from the less electronegative carrier, like NADH, for example, through these 4 proteins to O2, which is the most electronegative because it's so close to fluorine on the periodic table, okay? This electron transfer, this redox, causes the protein to move H plus from the matrix to the inner membrane. It's floating out here, but then it's going to come back into the mitochondrial matrix through our ATP synthase, which is our big rotor here, creates this proton motive force, this hydrogen proton gradient, and that's creating our ATP. That is cellular respiration. I'm going to bed.